Okay, so this is chapter 11, part 7. So we're moving on here to kind of find our way into all the steps and all the phases involved in an action potential. So the first thing we're going to talk about is a graded potential, and these are basically short distance signals. And they result from, like, what causes a graded potential. So just to give you some backstory here, an action potential is an actual firing of a neuron to cause something to happen, whether it be a muscle to contract or a gland to secrete a hormone. So a graded potential is kind of, it doesn't, an individual graded potential is not going to cause something to happen on the other side, or meaning an actual firing of the axon or the neuron. So graded potential, therefore, are referred to as short distance signals. Now, if enough graded potentials come in, we can add them up to, and they can combine to make an action potential or to create an action potential. But generally speaking, graded potentials, by definition, are not going to cause an action potential on its own, or a firing of a neuron on its own. So what is a graded potential? Basically, it's when ligands or chemicals bind to the receptors. If there's slight changes in the charge across the membrane, they can result from a mechanical stimulation, something pressing against certain mechanically gated channels, temperature changes, and then sometimes spontaneous change in permeability of the membrane. So for graded potentials, the magnitude varies from small to large depending on the stimulus strength or the frequency. They can be hyperpolarizing or depolarizing, just like what was shown in this picture here, but we haven't met threshold in order to fire an action potential. So a graded potential is just a slight change in the membrane potential, not reaching threshold, which we'll talk about that a little bit more as we talk through this. So like I said, graded potentials can summate or add onto each other, causing a more powerful signal. They spread or conducted over the plasma membrane in a decremental fashion. They rapidly decrease in magnitude as they spread over the surface of the plasma membrane. So they kind of fizzle out. That's basically my way of describing them. They can cause the generation of an action potential, but only if threshold is met. And usually that is from, several graded potentials basically summating or adding together to meet threshold. So just to clarify, every time a graded potential happens, it's going to slightly hyperpolarize or slightly depolarize the cell membrane. And as you know, if something hyperpolarizes or depolarizes the membrane, then either sodium or potassium are moving back and forth. So if it's only happening in small amounts, in a graded potential amount, then it's not going to add up to this magic number that we refer to as threshold. The magic number, by the way, is negative 55 millivolts. So if we are generally speaking around negative 70 or negative 80, and we just get, enough graded potential to, say, get to negative 60, right? Because negative 60 would be up here, and then negative 50 and so on. This isn't to scale the way I'm doing this, but then, if it doesn't meet that negative 55, then it's not going to fire as an action potential. It's just little changes, basically, is what a graded potential is. Again, they can add up and cause an action potential, but that's only if threshold is met. Somewhere, write this in your notes somewhere. Threshold is negative 55 millivolts. Threshold is negative 55 millivolts. And that's the magic number that allows an action potential to actually fire completely. Okay, So action potentials are ways that neurons communicate. Graded potentials can summate at the trigger zone where threshold could be met, which is negative 55 millivolts, and that's how we abbreviate it there, the little m and a capital V. When an action potential fires, we have the depolarization phase or depolarized phase, followed by the repolarization phase. We didn't talk about repolarization earlier. Earlier, we were just talking about which way the membrane potential can go at the start, at the resting membrane potential. Once we're at the ready state, it can go up or down, basically. It can depolarize or hyperpolarize. Those are the only two options from the beginning. So if we have an action potential and the cell membrane is depolarized, then from that point on, there's a series of events that'll happen to get it back to get that membrane potential back to resting membrane potential. So depolarization phase is followed by the repolarization phase. We depolarized it, now we had to repolarize it, right? And remember that we also refer to, just give you some backstory here, the resting membrane potential. They refer to the membrane as polarized. So during an action potential, the polarized membrane can become depolarized, which is when sodium enters through those voltage-gated channels, enters into the cell, and the cell membrane becomes more positive, somewhere around positive 30 millivolts, because that sodium brings with it its positive charge. After that happens, we go into the repolarization phase, and that's because potassium gates open and potassium leaves through their voltage-gated channels, and that causes the membrane potential to become more negative because potassium is taking with it its positive charge. So the inside was negative. Now we're losing positives from the inside. It's going to become more negative. So when I said earlier that the potassium gates were kind of like the slackers, and they're slow to open and slow to close, because during an action potential, the sodium gates and the potassium gates are actually prompted to open at the same time. The sodium gates are really quick, super high achievers, we'll say, but the potassium is like, yeah, I got this, I'm going to take my time. So the potassium gates take a while to open, even though they're both kind of triggered to open at the same time. So because of this, the potassium gates open slow and they close slow. So this means that when potassium leaves, the gates are going to stay open a little bit longer than we want, and that's going to cause the cell membrane to become hyperpolarized. And that's from the potassium gates remaining open a little bit longer than anticipated. And so we went from, when we're repolarized, we get to right around negative 80, negative 70, somewhere in there. And because those potassium gates stay open, we get even more negative inside because even more potassium leaves, losing even more of their positive charges. So that's the basics of an action potential. The cell membrane becomes it's polarized, then it becomes depolarized, goes to about positive 30 millivolts. And remember, at the polarized state, we're around negative 80, negative 70, somewhere in there. When it becomes depolarized, it goes to positive 30. To repolarize it, it goes to about negative 80. And then the gates stay open, becomes hyperpolarized, kind of overshoots what it wanted to do, and we get to all the way to negative 90 millivolts. Now, how do we get from negative 90 millivolts back to resting membrane potential, back to that polarized state, which is somewhere around negative 70, negative 80 millivolts? Well, resting membrane potential right here is restored back to around -80, -70, somewhere in there, through the existing leak channels for sodium and potassium, and also the sodium potassium pump. I don't know, I can't remember if I have mentioned this already, but there's a lot more potassium leak channels than there are other leak channels. So that means potassium is leaking back in to the cell at higher rates than sodium would be leaking out. So all or none principle, you're going to be asked this on the test as far as what does it mean. And the all or none principle means that no matter how strong the stimulus, as long as we meet threshold, as long as we get enough stimuli to meet threshold, to bring that membrane down to -50 or up to -55 millivolts, then an action potential will absolutely occur. There's no half of an action potential. There's no small action potential. It's either going to fire or it is not. It's like flipping on a light switch. If the electricity is hooked up to it and it's in the ready position, as in all the electric is on, the electric company is sending electric to your house, and you flip that light switch on, the light doesn't kind of come on, it comes on. And that is what the same idea here is. An action potential will either fire completely or it will not. All or none principle means as long as we meet threshold, an action potential will occur. Okay, so I'm going to pick up a little bit more on action potentials in the next video in part 8.